Hello, my name is Curtis Lawrence, and I am responsible for implementing the functionality for Task A of Assignment 3. This included creating a test mode function for finding plots, as well as a non-test mode function, validating the plots, terraforming, wall placement, and then grouping plots to find waypoints for later use in subtask C. Now to begin, I will start by discussing my finding plots function. This required me to create two functions that essentially serve the same purpose. However, one was for testing, as you can see here, this functionality all the way down until here, line 249, was essentially used to create an environment that would allow for my black box testing. Now, for the testing, depending on what number the user would input into my function would determine which of my 8 tests were to be run. For example, if the user input test number 7 or test number 8, this would allow them to essentially see whether or not certain plots are within the village bounds or outside of the village bounds. Additionally, test number 1 and 2 would determine how much water content there is within a certain plot and whether or not that was a valid amount of water. Moving on, test number 3 and 4 would determine how slope heights would affect which plots could be placed where. And finally, test number 6 and 5 were to determine whether or not a plot was intersecting another plot. The main difference between my test mode version and my non-test mode version is how plot sizes are being looped through, as well as how we are looping through the village to determine where plots are going to be placed. For instance, we start off with a plot size of 14 for the test mode. We then are going to loop through the Z coordinate in increments of 5, and then we will do the same for the X coordinate. Now, once our plot size reaches 20, we are going to check if adding 1 to it would increment it past 20, which is beyond a valid plot size, and then we will reset it back to 14, and the process will repeat. For my non-test mode version, it was relatively similar to my test mode version in all of its functionality for checking water content, checking whether or not plots intersected other plots and the border, and etc. However, there was a random aspect that needed to be implemented, and that's where the main difference is. For instance, the village size of the non-test mode version is determined randomly, as you can see here, for both the Z and X axis, and the plot sizes are also determined randomly. The function will essentially sample up to 1,000 plots randomly within the village. So it will take 1,000 random coordinates, and from there it will determine whether or not those are valid coordinates for a plot to be placed on, depending on whether or not it meets all of the requirements as previously mentioned, slope height, water content, all of that. For the terraforming aspect of task A, my terraform function would take in a reference to a vector of plot objects, as can be seen here, that was returned by my plot validation function. It would build the foundation for the plot using stone and dirt, and then it would terraform the border surrounding the plot using a linear function, as can be seen all throughout here. Now, this linear function would essentially find a target height for the terraforming to build up to, shown here, and this is determined by its relation to how close it is to the edge of the plot, and that is essentially how the plots were being placed and then being terraformed. For building the village wall, I had to separate it into two separate functions, one for actually placing the wall and another for building the wall. Now, while they might sound similar, they are different, and I will get into that in just a moment. Now, the reason I did this is because there were some time issues when I was initially just building and iterating over the village wall, and it ended up being quite slow, in some cases upwards of 5 to 10 minutes when trying to complete the wall. The wall would initially check if there was any foliage or trees or anything that might be along where the wall was going to be placed and remove them just to prevent any sort of weird wall being placed on top of a tree. Now, as you can see here, each section of the wall is being built individually. Now, how it's done is each column of the wall is terrain aware. And what I mean by that is it will check a 5x5 radius around the coordinates of the column of the wall that is currently being checked in this section here. And it will find the highest block in that section, and whatever the highest block is in the section, it will build up to that height, and then beyond that height, plus 4. And that is essentially how I created a wall building function that is terrain aware and will build up 4 blocks higher than any other block in a 5x5 radius. My function for grouping plots essentially iterated all of the available plots that we had and would continue this until the plots were empty. Now, essentially, while the current group that we are working with or adding plots to was less than 3 in size, and there were still plots in the remaining plots, we would be pushing these plots into that group. And in the event that there would be, say, one plot maybe left over at the end, we have this check down here. And what this would do is if the final group in the vector of groups had a size of 1, so there was only one plot in that group, it would find the group that has the closest average to that plot, and it would add it to that group. And that is essentially how groups of 1 would be added to the nearest group, just to prevent those little groups from having no waypoint at all. The final aspect for task A was finding and validating waypoints. This was done by first grouping available plots into groups, creating a vector of waypoint objects, and then for each group in the vector of groups, creating a waypoint object that would allow us to, in future, use them for path building. Waypoints were found by averaging out the midpoint of each plot in the group, checking to ensure that the point was not within any plots and adding it to a vector of waypoint coordinates if it was valid. So essentially, it would find the average, as shown here, of each of the midpoints in the group that we are looking at, and it would then determine if it is valid, meaning whether or not the point coordinate of the waypoint was within any sort of plot. In the event that a coordinate was within a plot and therefore invalid, the program would then check within a 4x4 radius around the original coordinate and attempt to find any other sort of waypoint that could be considered valid. In the event that no valid waypoint was found, an error message was to be printed stating that no valid waypoint could be found, and the resulting waypoint was set to 0, 0, 0. After this, all of the waypoints that had been found were added to a vector of waypoints, and they were allowed for further use in Task C for path building and waypoint building.
Hello, my name is Danilo, and I was responsible for the development and implementation for Task B. As a quick overview, I will now run the completed function in testing mode to demonstrate the final result. As you can see, the function begins by resetting the area around it, before building a layout for the building based on either plot sizes acquired from part A, or in test mode, a hard-coded plot. It then uses a subdivision algorithm to split the initial box into as many different rooms as is possible given the brief's restrictions and plot size. From there, another algorithm will iterate through the completed building to detect and map each subdivision, in order for the room decoration algorithm to adjust and enact itself according to each room's unique size and features. And finally, a roof is built on top for the building aesthetics. Given both the high flexibility and restrictiveness provided by the many random elements of this task, each house created is significantly different from the next, with different wall subdivisions, room allocations, and sizes in terms of length, width, and height. The program can adapt to support all of these as both random allocations or specific given values when it comes to test cases. So, how does the program work? Upon entering the build buildings function, the first act of the program is to call the test mode select function. This function determines whether the function was called in test mode or not, and if so, which variables to update and change in accordance with the command line input. For the purposes of this overview, I'll be describing the processes of non-test mode functions, thus this function would make no changes to the plots vector. Resuming in build buildings, the function first checks if the plot size given are valid, as each side must be between 14 and 20 blocks inclusive. Any that are not are ignored and the program moves on, leaving an error message. From here, the initial house is constructed, with a height decided using the standard random device put through a uniform int distribution function, as the random device is non-deterministic as the brief requires, returning a height within the outlined maximum and minimum of 5 and 20. A side to start on, either X or Z, is also picked at random using the same method as per the brief. Once a side is chosen, the program enters the subdivision algorithm, which recursively calls on two functions, getWallX and getWallZ, to provide wall locations inside the room that the subdivision algorithm can build until no valid wall positions are left. In order to maintain efficiency and meet the requirements of total randomness, the uniform distribution is restricted to a set of valid values, determined by a vector between the minimum and maximum X or Z values of the plot. Each time a value is checked and found to be invalid, that position is removed from the vector, making it impossible to retrack randomly, saving significant time and resources. As walls begin to populate the area, the subdivision algorithm iterates through the building, hitting each inner wall as they are built and checking values along the interior to ensure no possible wall locations are missed. This occurs recursively multiple times until both getWallX and Z fail to find any wall locations, ensuring that the room is subdivided as small as it can possibly be, returning 0 to the buildings function and thus ending the while loop. As a bonus, doors are automatically built in as walls are being constructed, ensuring every room is accessible from the entrance point and saving resources that would have otherwise been wasted on a door implementing algorithm. From here, the function findRooms is called. This function creates a path which iterates through the build from the minimum x coordinate to the maximum x coordinate of the plot. Each time it encounters a wall, it automatically iterates to two opposite corners within the room, thus defining it between 2 points, which are sent to the room decoration algorithm to populate them with furniture. Upon reaching the maximum x coordinate, the function iterates 3 positions up on the z-axis and resets its x position, ensuring it will never miss a room even if the subdivisions are chaotic. Any rooms then which are found to be between the previous coordinate points are ignored as duplicates, and the function keeps iterating until it reaches the maximum z coordinates of the building, signaling it has found every room. As rooms are found by this algorithm, their opposing corners are passed into the decoration function. There are 4 possible types of available decorations: the bedroom, bathroom, kitchen, and lounge room. Room types are picked at random, and each one is designed to be flexible, allowing them to be applied to a variety of differently sized rooms. However, not every room type supports every room shape, and thus the same vector method that was implemented in the getWallX and Z functions is implemented here, to ensure no room type is tried more than once. Thus, utilizing the corner coordinates found in the findRooms function, a valid room type is chosen and adjusted in its design to fit the specific size and shape of the room, leading to multiple different combinations and even added furniture in the case of larger rooms. And finally, after decorating each individual room, a roof is built using an iterating fill function, allowing for the 4-way slanted roof style. Testing the function was the easiest part, as present errors often availed themselves with little to no changes in the setup. However, as the program became more defined and structured, I made consistent use of test cases, both the ones listed in my portion of the testing MD file, my black box testing, as well as custom test cases which did not entirely fit the restrictions of the brief, such as doubling the allowed size to 40 on each axis and observing the result. By testing edge cases and pushing the program beyond its expected parameters, I was able to catch many bugs and logic errors, as well as restructure major parts of the code to ensure they ran smoother or were better at detecting possible logic errors. Defensive programming is probably the most apparent style in my code. Throughout the decoration functions especially, each decoration contains numerous checks all around its expected build location before anything is made, ensuring no clashes with existing doorways or walls. On top of this, each one has anywhere between 2 to 4 alternate locations built into the code, should the preferred one become unavailable, with some simply iterating along entire axes until a valid location is found. And if one is not, the program simply moves on to a new room type instead of trying to force a creation. Furthermore, the rigorous checking with the getWall functions, wall subdivision functions, and findRoom functions ensure that it is impossible to build a wall in an invalid location, whilst also ensuring that not one valid location is missed. In terms of structural programming, each aspect of the house building method is separated into its own function to reduce confusion and keep the buildings function clean and uncomplicated. Each function is also given one specific purpose and does not exceed that scope, ensuring that functions are not reliant on excess filler code in main, or that one function can proceed independently of another without breaking the entire program. And finally, most of the defensive programming within the code is built on the principle of programming by contract, ensuring the use of pre- and post-conditions to avoid unexpected results. As a result, I was able to build a robust, near error-free function which achieves its intended purpose with both efficiency and effectiveness. Both efficiently and effectively.
Connection. Connection is what brings people together. It makes beautiful festivals, and families, and friendships, and fun. So if we as a people are so connected, so too should our places in which we call home. Connecting the village together with intelligent path networks, beautiful structures, and state-of-the-art gravel?
Hello, my name is Teige and I worked on Task C Pathfinding. In all seriousness, in this video, I hope to share with you the work that I did in this assignment. I'm very proud of it. I would like to discuss my thought process, share things I've learned, and demonstrate that not only have I completed my task, but gone above and beyond. I'll be covering the main components of my implementation, which includes my custom container classes, my testing, research, and implementation of a pathfinding algorithm, how I connected all the waypoints together, the waypoint abstract data type and programming by contract, waypoint structures, testing, and finally some examples of defensive programming and structured programming. For task C, I needed specialized data structures to make my A-star pathfinding algorithm efficient. And yes, that's right, I said A-star. We'll get to that in a second. I designed these two custom abstract data types from scratch, path tree and linked list. So path tree represents the search space as a tree structure, enabling efficient path reconstruction. Linked list, on the other hand, serves a dual purpose in my pathfinding, acting as both an exploration queue and also a priority queue sorted by cost. In A-star, we explore thousands of potential coordinates, maybe hundreds, and path tree organizes these nodes as a tree where each node stores a coordinate, its parent, its depth, its cost, and its cost to reach it, as well as any of its children. This parent-child relationship is crucial. It lets us backtrack from our destination to reconstruct a complete path. Going forward, we can see that we can add a child, remove a child, and get a number of children. Both adding and removing has defensive programming written into it, and let's have a quick look. All right, so here is some defensive programming in action. Before adding a child, if we have exceeded the max neighbors, then we're going to delete the child to prevent memory leaks, and then throw a runtime error, which lets the caller know that what went wrong, and so we don't leave an orphaned memory. Here is a path tree. I'll quickly talk about safety. If we have a look at the deconstructor, what this does is it deletes subtree of the root. What delete subtree does is it goes through each of the children and deletes that node. Now this is the heart of path tree. Once A-star finds a destination, backtrack path walks up the parent chain to reconstruct a completed path. Notice the defensive programming here. We check if this current is a null pointer, aka if depth was too long or if the parent was somehow a null pointer. And if that's happened, we're going to clean up our path and let the caller know that we have had a big failure and kind of explain it a little bit more there. This structured approach, a clear loop, single responsibility, robust error handling is what makes my code reliable, readable, and structured. Now to the linked list. It's pretty simple. It's pretty much your linked list. However, you might have remembered I mentioned that we actually have some sorting. You'll also notice some defensive programming here, not trusting user input. So if for some reason the data that was inputted was null pointer, yeah, this code is just not going to run. It's just going to skip to the end. That's it. So to summarize, path tree maintains parent-child relationships for path reconstruction. And the linked list is, well, a linked list, but also sorted and also can be used as a queue. Together, they make the A-star pathfinding efficient and reliable. Talking about A-star, let's have a look how these structures were used in the pathfinding. Now, onto the titular part of my task, pathfinding. After trying out the breadth first search, I found it isn't the best. It's slow and was often taking minutes to run. So I looked at other methods, other ways I could speed up my program, and I came across Distro's algorithm and then A-star algorithm. Now what I've implemented here is A-star. It is pretty much A-star and there isn't anything too different, but it has a slight modification, and I want to focus on that, and that is in the cost. As you can see, we have some pretty basic A-star stuff. We have G cost and H cost, depth, so we make sure that we're finding the shortest path. However, we have some extra cost here, and that is to do with height change and water. According to the requirements, paths should avoid changes in height. Of course, it is often necessary for a path to have changes in height, but they said prefer a flat route. The way I interpreted it is that if there's an option between going up one block or going around it by one block, then just go around. But otherwise, just go over that hill. I mean, it doesn't cost too much. And that is why in this code, you can see that the height, when we multiply by this height change cost mult, I've actually set it to be just a 12.5% increase. However, water should be avoided at all cost. And that is why the cost of water is so high, a 10 times multiplier. This one's quick. For the connecting the waypoints, I just used Prim's algorithm. It was what was said in the assignment requirement, and it worked really well. When you program by contract, you're essentially creating an agreement between two programmers, and that's what Curtis and I did. With the waypoint abstract data types, as you can see here, store a coordinate and a pointer to the related plots. A simple and clear interface, yet vital for task A and task C to interact with each other. The coordinate is the waypoint coordinate, and the plots are the related plots that we use to calculate that coordinate. Now, Curtis has done some other functions and code in here for his own task A purposes, but for me, all I needed to know was the waypoints and the buildings it connected to, because then I could just connect the buildings by going through each waypoint, then each of its related plots, and connecting the buildings that way. Now in this testing environment, you can see the different waypoint structures that I created for this project. They're pretty simple. All it is placing some blocks, but I decided to put it into a separate file to maintain the modularity and readability of the code. I created 15 plus comprehensive tests to make sure that my pathfinding algorithm worked well. And we'll look at some of them right now. Here I'm about to run test number 2, which tests a straight line in the x-axis. Go on ahead and click enter there. Oh, we're looking at the wrong side. There we are. It's been created. I'll do test number 3 as well, just so we can see that happening. Here we are. Yeah, so you can see the path being made like that. I will also show, while we're here, test number 1. So my test also covered abnormal data as well. So test number 1 talks about abnormal behavior where two waypoints are on the same block. It actually deals with that properly and creates a proper path, which is 1 block wide, and then creates the 1 waypoint. I also set up tests where we have different heights, as you can see right here. So it climbs up by 1. We have climbing over a hill. Tested edge cases. Other abnormal situations, such as when a block is in the way, just like it is here. Scenarios such as it being completely surrounded by water, a waypoint being surrounded by water, like in this scenario. Even in my testing, I account for scenarios where there is no possible path, which is happening right now. The code is basically looking at the entire selection here, because it's all within that 200 village size, and you can see, there we go. So instead of, when it can't find, I should say, the complete path, it instead shows an error and an incomplete path, and it says an error in the terminal, and instead shows the closest path to our end goal. So, some final words to send you off. I just want to rein it back and focus on the things that I really want you to understand. I want you to understand I won't be on the specifications using A* instead of BFS for better results. I use my custom abstract data types, the linked list and the path tree for pathfinding, the defensive programming, constant null pointer checks, bound validation, error handling. My structured programming, I had lots of functions that were all modular, clear separation of concerns, programming by contract with Curtis from task A, with the waypoint abstract data types. Comprehensive testing, more than 15 test cases covering a wide range of different edge cases, and real results, as when you run it, you'll see a real working village with paths. Thank you so much for your time. Have a good night.